Problem number 44. We want to verify Green's theorem for this integral right here. Let me put a little C right there, where C is the triangle that goes from 0, 0 to 1, 0 to 0, 1 in a counterclockwise direction here. Okay, how do we go about doing this? So one way is in part A, we want to evaluate this directly as a line integral. So that's actually going to be 3 separate line integrals here, C1, C2, and C3. C1, C2, C3. For C1, and C2 and C3, let me just start off by writing down parameterizations for each one of these curves. So C1, call R1 of t, can just be t is going to, let's see here, x goes from 0 to 1, y stays put at 0, so there's a parameterization, t goes 0 to 1. R2 of t, let's see, we need this to go from y goes from 0 to 1 as x goes from 1 to 0. So I think this should do the trick. R3 of t should be, let's see here, x stays put at 0, y goes from 0 to 1. I think this should be the parameterization here. And then we should know here that, okay, let me just write down the derivatives real quick. R1 prime of t is 1, 0. R2 prime of t is negative 1, 1. R3 prime of t is 0, negative 1. Okay, so let me go from here. Okay, let's start calculating out some integrals. So integral C1 of f dot dr. Our f here is going to be 2y squared comma 2x. So let's see here, we need integral from t runs from 0 to 1. F of R1 of t would be, let's see, we replace y with 0, and we replace x with t. So that's f of r of t, dot product r1 prime of t, 1, 0 dt. 0 plus 0 is 0, so this integral is 0. Okay, how about C2? Well, this be a little bit more interesting. Okay, f of r of t, we replace, let's see here, 2 times t squared, and then 2 times 1 minus t, dot product with r2 prime of t, negative 1 comma 1 dt. And so this is going to equal, let's see here, the integral from 0 to 1 of negative 2t squared, and then plus 2 minus 2t dt. When we take antiderivative of this, we end up with negative 2t cubed over 3 plus 2t minus t squared, plug in from 0 to 1, and so we'd end up with 2 minus 1 minus 2/3 is 1/3. Okay, for the integral along C3 now is going to be integral from 0 to 1, f of R3 of t. R3 of t is right here. So 2 times 1 minus t squared, comma 2x, x is 0, dot product with the derivative here, 0, negative 1. And oh look, 0 plus 0 is 0. We just have 0. So The circulation around, calculate out as a line integral in 3 chunks, is 0 plus 1/3 plus 0. So this answer here is 1/3. Okay, so that's half of the problem. The other half is saying, well, integral over c f dot dr is going to equal the double integral over the triangle r, they call this r here, of the partial derivative of this with respect to x. So like this is our m and this is our n, so partial derivative of n with respect to x. So that's 2, minus the partial derivative of m with respect to y, and that's going to be 4y dA. Okay, we need some bounds on our integral. I think we can just say that x runs from 0 to 1. Y, for a particular value x, goes from 0 to 1 minus x. So these will be our bounds here. 0 to 1, 0 to 1 minus x, integrating 2 minus 4y here, dy dx. Okay, integral from 0 to 1, that's antiderivative here would be 2y minus 2y squared, plug in 0 to 1 minus x dx. So we'd end up with the integral from 0 to 1 of 2 times 1 minus x is 2 minus 2x, minus 2 times 1 minus x squared, so that should be minus 2 plus 4y and then minus 2y squared. Oops, those y should be x's. dx. Okay, those cancel. That becomes 2x. So we are integrating here 0 to 1 of 2x minus 2x squared dx. Antiderivative to this would be x squared minus 2x cubed over 3. Plug in from 0 to 1. 1 minus 2/3 is 1/3. And yes, didn't mess up anything. That exactly matches the answer we had before. If we didn't get the same answer there, that would tell us something had gone wrong.